In our second video on region between two curves, we're looking at more complicated situations. So our goals are to be able to find that area in more complicated situations. For example, when lines cross several times. The second thing we're going to look at, and it's our second goal, it's basically showing the role of technology, so how it can help us with the graphing and help us verify our solution, which is required in some assessments and in day-to-day life in maths classroom. If we consider the graph there, it's not a particularly well-defined function, but it's a generalization and it's showing a more complicated situation, and there's 4 intervals that we need to consider. And the 4 intervals create 4 bounded areas, 1, 2, 3, 4. So if we're looking between ultimately A and B, we need to split it into all of those sub-intervals. So if we take them one by one and apply the properties of integration that we looked at previously, and we have names of the functions g and f, or f and g. We have interval from A through to C1, and we can see there if we follow it, and they haven't, well, I haven't helped you much because I've provided you with a graph where the lines are the same color, but if we trace through, we've got f is greater than g in that first interval. Hence the expression f of x take g of x between A and C1. All right, and now these are all going to be added because what we've done, we've taken care between each interval is to put the functions in the correct order with the high minus the low. So we don't have to worry about any signs, subtraction signs and stuff like that. So, and area in this sort of context is always considered positive. It's not like some of those area below a curve or between a curve and an x-axis where some areas are considered positive and some are considered negative algebraically. We don't have to worry about that. All areas, all of these brown zones are considered positive. And what we have to do to get the correct value with the correct polarity is get these functions in the correct order. Now we can see in the second interval there between C1 and 2, which is, sorry, C1 and C2, say it properly, we can see that, well, if we follow it, f is lower than g, so it's g of x take f of x, and we continue on right up to the third and the fourth intervals. An alternative is to not worry about that order, but just put the absolute value signs around it. You can see there, it's always f of x minus g of x. That's fine as well. You can see the intervals are the same for each corresponding part. So if we put absolute values around each of these terms, they will come out positive. Either way, it's correct and appropriate to do it like this. Let's look at an example that will help clarify our 2 learning goals. So find the area of the region enclosed by the graph of, the first one's going to be f of x equals x cubed, and the second function is going to be g of x equals x. So we have a cubic and a linear function. Okay, so what we need to do is look at a diagram, and we can get a bit of a sketch happening. Okay, so by hand sketch is recommended, and well, if we have our scale 1, 2, and so on there, perhaps I'll make that scale like this actually to use the space a bit better, and we can now put in g of x, because that's very easy. Y equals x is a very easy graph to draw, and you probably know by now the graph of y equals x cubed, so it's got an inflection point being a cubic. I'm going to use a different color, and I'll put that in now. So it kind of goes like that. It's a sketch after all, and like so. So that's y equals x cubed, or f of x. So the bounded areas, the regions, there's 2. And there's an interval where x cubed is greater than x, and then there's another interval where x is greater than x cubed. So it is one of those more complicated situations. Now, to use technology, we can do a couple of things. Let's say we're using a TI Nspire calculator. We can basically get our graph. If you weren't sure about the graphing it in, if you're allowed to use a calculator in your context, use it, and you can basically do the following. So we can enter in F1 equation, so using your graphing facility, we can enter in x cubed. So x cubed, enter that in, and then we enter in x for g of x. We got the cubic and we've got the linear graph. Okay, need to zoom in a bit. Okay, so we can see the two graphs. We've got a good zoom. We can look for our points of intersection first of all, like so, and we choose 4 and look for your lower boundary, upper boundary, and we get a point of intersection. Then we repeat. Okay, choosing 6, then 4, and likewise. And we'll get our second one. Now to repeat the same menu, but this time we are going to choose 7 bounded area, 7, and we look at our bounded areas. Okay, see how it says point intersection? Click on that and then take it to the upper one. You see the bounded area, and you can possibly see the a number. It's around about the origin. It's increasing towards 0.5. And when this other one says point of intersection, we know we've got the right spot there. It's a tad fiddly. Needs to say point of intersection. Come on, work for me here. Okay. And it's a bit of, there you go. Okay, and that's gone up to 0.5. That number moved up. So it looks like the answer is going to be 0.5. The other way of doing that, that gives you a graphical look, and some calculators will calculate the area. The other way is to go into your algebra menu in your main part of your calculator and solve or polynomial tools number 3, and find the real roots of a polynomial number 2, polyroots, and we go x cubed minus x, the difference between the two functions, and the variable is x, so we go comma x and close the bracket. Okay, so that those three numbers, -1, 0, and 1, are the 3 points of intersection for the two curves, the orange and the blue curve. All right. The other thing we need to do now is the following. We can do this by hitting the templates button there, like so. And we can see the two templates we want. First of all, we want the integration template, the definite integral, and we want then the absolute value on there, the two we're going to use. So this one first. Hey, I didn't press U. Hey, look, live bloopers here. All right, so the overall interval we're looking at in entirety is from -1 through to 1. So we've got from down here, if you can see my cursor, right through to there. Okay, so that's what we want. So that's what we're going to set our integration to on the calculator, and it's got an absolute value around it. So let's have a look at how that works. We've got -1 to 1. Now here's where the absolute value comes in. Okay, and it's x cubed minus x. So the integral from -1 up to 1 of the absolute value of x cubed minus x dx. and we get that. And look, 0.5 again. So now let's do it analytically. So first thing we need to do is find our intersection points analytically. This is the important part, really. So the two functions are equal to each other at their point of intersection. So we have the equation to solve x cubed take x equals 0. Now factorize that. We've got, so we have x outside of x squared minus 1. So using the null factor rule, x will equal 0, or that's for the first part of the product there. For the second part, the x squared minus 1. So x squared equals 1. So x equals plus or minus 1. So there's actually 3 solutions which corresponded to our technology that we found before. So now let's set up the integration, regardless of whether you use the absolute value signs or not. I'm going to just for a bit of variety, I'm going to use the first method where we just work out what's on top and what interval. So basically the bounded area required is, we're going to look at that first interval there. So that's from -1 through to 0. Okay, and our polyroots before verified that, or pre-verified that. And we've got the cubic above the linear, so it's x cubed minus x dx. And added to that is the second part of the bounded area, so that's between 0 and 1. Now the linear is on top, so it's the linear minus the cubic. And we go ahead now and I'll continue on. And we go through with the usual process and we get 1/2. So the area of the region is 1/2 units squared. What if we have a situation here where we have the bounded area between y equals cos x and y equals sine 2x? So this is the final part of the video. It's a different sort of pair of functions. So we need to realize, and by the way, we are going between 0 and pi on 2, just to clarify that. So there are 2 bounded areas. There's roughly shaded, there's that one, and then there's the second one over yonder. Oh, I shouldn't have gone over the line there. Okay, anywho, I don't have very good colouring in pens. I'm sorry about that. Now you can use all of those calculator functions to verify your work with this, like polyroots and so on. I'm going to analytically now find the points of intersection. So we've got cos x equals sine 2x, which is 2 sine x cos x. That's using one of our trig identities from our formula sheet, but we've already covered the maths for that. So cos x equals 2 sine x cos x. Moving on, we've got 0 equals 2 sine x cos x minus cos x. Take the factor of cos x out on the right hand side, and we have 2 sine x minus 1 inside the brackets there, and we still got 0 on the left side. So null factor law works with trig functions, of course it does. So one of those 2 terms in the product equals 0, or both equal 0. So if we have cos x there equal to 0, that's 1. And I'll put it over here, 2 sine x minus 1 could equal 0 as well. And we have that 2 sine x equals 1, and so sine x equals 1/2. Okay, we have 2 results there that we can use. Now, to each of those little equations, there could be more than one answer. Let's analyze it a bit now. Because our interval is between 0 and pi on 2, okay, that's where we've got to restrict the domain. So x is restricted between 0 and 2 pi. So thinking for values of x such that cos x equals 0. Now we know in the between 0 and 2 pi, cos of pi on 2 and cos of 3 pi on 2 equals 0, but between 0 and pi on 2, the only value for x would be x equals pi on 2. Okay, and if we look at that restriction over here, we have pi on 6 is the only solution there. So there's our x values for our points of intersection. Moving back up to the diagram to see what's happening up there, pi on 2, pi on 6, well, the pi on 2, that's the end of the interval, so we don't have to worry about that one. That's already sorted. Pi on 6 is this one. Could be easily verified with technology. Okay, and when we're looking at how these increments are working here, these are in sixteenths of pi. So if we look at that'd be pi on 16, pi on 8. So that's pi on 8 between pi on 8 and pi on 4. Pi on 6 is a reasonable answer, and it fits somewhere between that. Okay, so it seems all good. Now let's set up the integration. So it's from the first part is from 0 to pi on 6, and just check if we're going to look at what's you could use the absolute values. I'm going to use just working out which functions on top or bottom. And if we do that, we can see that the cos value is on top of the sine 2x function, okay? Or you could just use the absolute value and just, doesn't matter what the order is as long as it's consistent, I suppose. So absolute value could be used there, but I'm going to go for cos x minus sine 2x. So sine 2x dx plus from pi on 6 to pi on 2, pi on 6 to pi on 2. Let's look at the graph again. So from pi on 6 to pi on 2, the brown area, we look through there and sine 2x is greater than cos x in that interval. So we put sine 2x minus cos x. And we go forth and integrate that now. Okay, the first integral comes out as that. Now remember, the integral of sine is negative cos. Okay, so that's why that minus negative becomes a positive there in the middle. All these types of integration we've covered before, so you shouldn't have too much trouble with that at this point. And the second part now, and we get that for the second term there, and time to evaluate now. Substituting in the limits for the first term, we get that, and the limits subbed in for the second term, we get that. Evaluating the trig part for the first term, we get that. For the second evaluation of the trig terms, we get that, term 2 there. Oh, I've spotted a little error. I should have written a plus sign there because that's plus up there, and there should be plus here. Okay, so it makes that first term there 1/4. Working on the second term, so we get negative 1/2 plus 3/4, and that all comes out as 1/2. Like the previous question, 1/2, whatever the units are, squared for the required area